All right, people, we're going to record this one. Happy Friday afternoon. If you're in Mod 1 and you're like, what? Why are there all these people here? This is all the other people that go to Turing. And if you're all the other people that go to Turing, good job being at the right place at the right time. We are going to do some week 4 with Jeff time. Let's see. So when I think about these sessions, I like to use them to bring in some topics that I think are worth you having exposure to, or like a bit of knowledge about, such that in the future you might be able to ask smarter questions. Not that you're going to walk away and be like, well, I'm an expert in that now, but just have a little more context, stretch a little bit beyond our day-to-day web apps and whatnot. And so sometimes we talk about like some computer science things. Sometimes we talk about job stuff, career things, etc. So today we're going to do some computer science. I'm going to do it a little bit differently. I was going to do my document camera and like some paper and cards and post-it notes, but I decided, I'm gonna be high tech today. I'm going to use a text file, a plain text file. It's not an exciting text file, Jared. Don't get ahead of yourself. It's just a plain ass text file. It's got one question in it. Okay. And it's kind of like the central question of what we're discussing here. How many is this many? And it's like kind of a trivial question. Seems like very straightforward, but what I hope to illustrate for you over the next 53 minutes is that it's a little more complicated than it might initially present. And there are times that you might have different answers. Like, how could this number be different in different settings? I would be much honored if you would like take notes. I'm going to give you a little something a little different today. I was like, let's put a little quick code exercise in there. So I'm gonna give you probably about 3:30-ish, excuse me, I'm East Coast today. 1:30-ish, 1:40-ish Mountain Time. Uh Give you a little code exercise to work on for a bit. And so I'm gonna teach you some stuff. We'll do a little exercise and we'll come back together, wrap it up, get you out of here. That's the overarching plan. So let's talk about counting. Counting is like fundamental to things like commerce, right? Communication, hunting, survival, like all kinds of things that humans have done since the beginning of time. So, what is it like? How does that actually work? Most of us learn to count through kind of like the immersion osmosis approach, like someone told you counting goes like this, and you figured out some set of like implicit rules of how it should work. Then you tried those things, you probably got some of the rules a little bit wrong. People are like, no, 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 it's not called that, it's called this. And you moved on, you like make it work. You can probably count. I was talking with a 5-year-old yesterday. He's like, I can count to 115. And I was like, what's wrong with 116? He's like, well, okay, I guess I could keep going. It's like, yeah, it's beautiful. You can just keep counting once you get the system down. So how many is this many? I've got some periods here. You could think about goats. You could think about stars in the sky. I don't care. Whatever it is you want to count. You're like a maybe primitive man, primitive person of a trillion years ago. We have a number system that is called decimal. Uh, Decimal coming based on dec, being the Greek root for 10. And I want to talk about first like how decimal works, and then see how other number systems work differently. So, in general, with a number system, we use symbols to represent quantity. So, we're going to talk about like symbols and quantity. Just for a second, I was like, damn, I didn't think about like my typing and my spelling in this plain text file. So, I guess you can laugh at me or whatever. We'll see how it goes. We're going to talk about symbols and quantity. What quantity to me in this context is going to mean like however many this is, that is a quantity. And there's more than one way to represent it. We represent it with uh, some symbols that we put together to make meaning essentially. Most likely, decimal is our default system because we have 10 fingers. And so therefore, like our fingers acting as our like built-in abacus, it makes it easy-ish if you're representing small quantities to like use your fingers. And my kids are actually making fun of me the other day because I go like this for three. And they're like, why do you do that? I was like, I don't know. Why do you do this? They're like, I don't know. And I was like, okay, don't ask stupid questions. Make three however you want with your fingers. But across these 10 fingers, you can represent 10. Maybe if you're real tricky, you could be like, oh, this is 11 and this is 14 or something like that. But our fingers, our toes lead us, nudge us towards base 10. We could potentially maybe do base 20 with fingers and toes combined. It's unclear that would really offer you any advantages over base 10. Also, we want people wearing socks and shoes. So, really keeping it to the fingers here with the 10. All right. Thank you in the chat for justifying my finger numeracy choices. How do these systems work? Okay, so in the decimal system, we have several symbols. They're very familiar to you. They do not inherently have any meaning other than their assigned and understood place in the number system. So, in a different reality track, I guess, you could like rearrange these symbols in some different order and achieve the same thing. Maybe not with four twice, but having seven in there as well. That would be just a fine number system. I've seen before like a link between the shape of these symbols and their quantity value, but I'm not sure I quite buy that. I think that's like revisionist. That like you can make an eight have eight angles to it, and nine have nine angles, and four have four angles and stuff. But yeah, I think we've more or less just picked some symbols and we had them decided that they would represent these quantities. So this mishmash misordered one is like not that helpful. Um, okay. So when we have that set of symbols, how do we actually use them? If I am trying to characterize how many this is, and I want to count it, okay, spoiler, it's 16. If I'm counting them and tracking them in real time, I go like, well, there's that many, but then there's that many, there's that many, there's that many, there's that many, there's that many. I keep going. I'm like tick, 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 eight, nine. And now at this point, I start to run into a problem, which is that I'm running low on symbols. And after nine is not, in fact, zero. Zero comes first. So I've misrepresented this with intention for you to point out that actually our symbol sequence goes this way. Okay. So really we had initially zero, then we started counting. We went one, two, three, four, we went five, six, seven, eight, nine. And at that point, we were then out. Oh, you can't see my way. Oh, so what y'all talk about here? You can't see. Oh, yeah, click on my share screeny thing. You don't really want to look at my face that much. It's like pretty plain. Okay. So if you got the text, and also apologies if I did anything in a confusing way. Zoom has changed up a little bit, and I haven't actually done any text editor teaching recently. So could be me also. Overall, I like the new interface. The buttons kind of remind me of Tron, and I'm into it. So back here, we've counted these quantities. We started, in fact, at zero, not at one. We went 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we run out of symbols. And so if you were treating this as a loop and you were going around, then you end up back at the beginning. Okay, 9 becomes 0, but now we're misrepresenting our quantity, right? Because there's not, in fact, 0. There's more than 0. We're just out of symbols. So now in the types of number systems we're going to talk about today, we use multiple symbols to represent quantities larger than our number of symbols. So you increment here. And then as we keep counting, we go 11, 12, 13, 14, 15, et cetera, 16, 17, 18, 19, until we run out of symbols again. We then loop back to our original symbol 0. And now it's a misrepresentation because we need to increment this quantity here to the next symbol. This fun game continues, right? We get to 29. The quantity after that, the ones place loops back to 0. Here we increment, continue on, and you're like, seriously, this is what we're doing? Yeah, this is what we're doing. 98, okay, 99. Now we again face the same problem where we run out of symbols here, so it loops back to a 0. We run out of symbols here, it loops back to a 0. Now what we have is not in fact 0, but is 100, and so we add another column out to the left, right? This is the premise of how counting in our number system works, in our base 10 number system. So, what would that look like? What would that process look like if used a different set of symbols? I'm going to consider base 12. And so in base 12, Josie, give me a letter that I can type on my keyboard without too much work.
J.
Jay, thank you, Joe. And Charles, give me a second letter.
Me,
Yep.
X.
Mm-hmm. X. Okay. Now, how do we count? Okay. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we're not out of symbols. So we go J and then X. And then we are out of symbols. So the X becomes a 0 and we add a leading 1. And then we go 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, 1 8, 1 9. We continue to not be out of symbols. We say J and then X. And then after X goes to 0, this has to increment to 2. We keep that pattern going. We maybe get up to 9 9. As 9 increments up, we don't return yet to 0. We go to J and then 9X. And then here, we still have more symbols for 9. So as X returns to 0, 9 becomes J, and then J1, J2, J3, J4, etc., J9, JJ, JX. X rolls over to 0, and then this J moves to X, X0, X1, X2, X3, X4, X5, X6, X7, X8, X9, making BMWs left and right. We go XJ, flip over to Toyota land, and then we go XX, and now this X moves, increments, wraps around to 0. This X increments, wraps around to 0, and you get to this 100. Now, is that 100? Not exact. I wouldn't use that word. I would call it 100 in base 12 because 100 in uh, this decimal. Well, let's see. 100 we know to represent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's take that and make it 20, 30, 40, 50. And this 100 collection of symbols in decimal rate is this many. But here in base 12, like when we had 10, that wasn't, it wasn't this many. It was actually, that's 10 in decimal. It was this many, 12, when we wrapped around. And so then this representation 100 is not 10 12s, it's 12 12s if you're speaking base 10. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this 100, I'm going to put some line breaks in here rather than making my stuff smaller. Ballpark there. Sure. This symbol, one followed by a zero followed by a zero, in base 10 would mean this many. And in base 12, it would mean this many. And hopefully you can see that's like significantly different. What if we flip the other way? What if we went, okay, let's talk base 8. Base 8 has a name. It's called octal. Again, from Greek root oct for 8, octagon, etc. So we don't have J and X. We, in fact, don't have 9. And a notable thing when we start to talk about bases is like base decimal up here, aka base 10, doesn't have a symbol for 10. Base 12 doesn't have a symbol for 12. This is a symbol like for 11, you decimal people would say. Okay, base 8 doesn't have an 8. It has 8 symbols, but one of them is not 8. Okay, so how does our counting go? 0, 0, 1, 2, 3, 4, 5, 6, 7. Can't go to 8. You're out of symbols, so you wrap back to 0. Now you increment this column. So now you go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. This wraps back to 0, and you get 20 or 2, 0. On up to 2, 7. Again, to 0 here. That goes to 3. Until some point in the future, you have 7, 7. And you increment 7, 7. This 7 becomes a 0. This 7 becomes a 0. Now you have 1, 0, 0 in base 8. So what does that mean? Well, our first 8 is like that. And then we don't have 10 of those, we have 8 of those. 2, 3, 4, 5, 6, 7, 8. And so 100 in decimal meant this much. In base 12, 100 meant way more. In base 8, 100 was a significantly smaller quantity than either of these two. Okay, keep the thinking going. What if you go further and restrict yourself to say, hey, let's do the minimum. Well, binary. Okay. And binary or base 2 doesn't have a 3, doesn't have a 4, doesn't have any of that. It also doesn't have a 2. It's only got 0 and 1. Now you apply the same rules, and I will say, even for me, they're like somehow more unnerving in the binary scenario than they are for base 8 or base 16 or whatever. And I think it's because you're doing this like carry increment really, really frequently every other time. So you start with 0, and you okay, after 0 comes 1, but after 1, I'm out of symbols. I'm back to 0. Therefore, I need to increment. And then when I increment this 0 to 1, that's valid. Now I want to increment it again, and this 1, this trailing one, end 1, moves back to 0. So this I want to increment to 2, but I don't have a 2. So it gets incremented to 1 to 0. And then we have the leading one over here. And then we increment this, valid. Next, this one goes back to zero. This zero becomes a one. Valid. Now we increment from there, and you go here. Valid. And then this one flips to a zero. This flips to a zero. This flips to a zero. And we end up with one. And I'm guessing there's a chunk of you who's like, I was down with what you were saying for a while, and then you just started saying zero and one like I'm some fucking robot over and over, and now I have no idea what you're talking about. So let's break that down. I'm gonna show you the leading zeros to make it maybe a little bit easier, right? In or some leading zeros, I should clarify. Like in this decimal number back here, 100, we could have put like a bunch of leading zeros, and you would have thought I was weird, but also you would understand that we're talking about this 100 number. The leading zeros were not significant. Same is true for all these number systems. But just to help you understand, I'm going to do a 4 digit. So my first value, my lack, my emptiness is 4 zeros. And then I have a single element. And then I have 2 elements. And then I have 3 elements, 4 elements, 5 elements. Oop, 1, 0. We're going to find out if I'm making mistakes here in just a second. Okay. Like perhaps the most boring of party tricks. I could count in binary. If I was going to add with those the decimal equivalents, that would be 0, 1, 2, 3. No, the most boring party trick is talking about CrossFit or veganism. 5, 6. God damn. Wrong total key. 7. If you're a vegan and do CrossFit, you can put your feedback in the weekly survey. Um, 12, 13, 14. Oof, I made it. 15. I watched Flight of the Conchords with my kids, watched a couple episodes. They didn't get it. I was like, I remember it being genius. So these are 4 digit binary representations. These are zero or excuse me, 1 or 2 digit decimal representations, just for you to see how it maps. But if you look carefully, if you look, for instance, here at just the trailing column, the ones column, if you will, you'll notice that it alternates 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. The second column is double that 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. The third column is double that 4 zeros followed by 4 ones, 4 zeros followed by 4 ones. The fourth column here is double that. Now 8 zeros followed by 8 ones. And if we continue on, the pattern would look exactly the same, just with uh, more leading ones and zeros. And if you kind of map backwards here, you would find the same patterns, right? Like you've seen, um, like on a if you imagine kind of a like multiplication chart type shape, but just if it was just counting instead of multiplying, you would see columns of repetition of like ones repeat over and over, and then twos repeat over and over, and threes. So these number systems, they even when we have more symbols, they repeat in similar ways. Coming back here to base 10, I've thrown in there some words like ones, like the ones place. Right? And these words come from uh, a computational mathematic meaning, if you will. And they are you're like, well, yeah, the meaning is like the ones place means one and the tens place means 10, dumbass. Like, yeah, I follow you. But like, why 10, why 100, why 1,000? And the reason is because the ones place is the base, in this case 10, to the power zero. And if you recall any, I don't know, maybe algebra one, anything to the power zero is one. So the tens place is called such because it's 10 to the power one, which is 10. And the hundreds place is 10 to the power two, which is 100. And thousands place is 10 to the power three, which is 1,000. So if you were going to make cute names down here in binary, like what are these spaces? Well, you would have 2 to the power 0 equals 1. So I guess we still have a ones place. 2 to the power 1 is, well, what is it? 2 to the power 1. Well, you could say 2 to the power 1 in decimal is 2. So that would make it the twos place. But we ain't talking about decimal. If 2 to the power 1, the quantity of that is like is actually in binary land is it's this many, which is why we would be led to say like a twos place, but there's no concept of two in binary. So really, this is just a tens place. And 2 to the power 3, because this is not 2, it's 1 0 in binary. And 2 to the power 3 would be like 1 0 0. And then you're like, wait, but there's a 2 over here. And I'm like, okay, fair. Because up here, we casually skipped over the fact that like 10 doesn't really exist. 10's a compound symbol. And it turns out that down here, it's the same thing. So if we were applying the same rules, I'm not saying you would necessarily do this. And when you're talking about binary, nobody's like, oh, in the hundreds place or whatever. Like that language just isn't used. But if you were going to apply the same uh, kind of derivation to get to the words for it, you would end up with the same answers. 10 to the fourth is 1 0 0 in binary right here. And that would be our thousands. Okay. I got one more I want to look at. And then I'm going to hand you over this little challenge for a few minutes. And part 5 here, we want to talk about taking this concept up here where I asked some folks for some random symbols. In order to increase our symbol count, let's increase it even further, specifically to base 16. And base 16 is hexadecimal. Again, Greek, like hex for 6 and dec for 10. So together it makes 16. You could argue like should be decihexamal, but no one will like you. So you should just stick with hexadecimal. And so our symbols here, I'm sure your mom would still like you and several other people. 3, 4, 5, 6, 7, 8, 9. Out of symbols in hex, we go A, B, C, C, D, E, F. What's special about these symbols? Nothing. We could have just as well chosen to represent them by like ampersand, hash, @ sign. We just didn't pick that. when the concept of hex was created, folks, or like at least in computer science space, folks decided just use the first six letters of the alphabet. It's confusing enough. Why make it even harder? So, how does hex counting go? We start with zero. We go zero, one, two, three, four, five, six, seven, eight, nine. From nine, we're not out of symbols. So we go up to A, we go B, C, D, E, F. Now we're out of symbols and we go to zero, one, zero. Octothorpe. Okay. Thank you, Lydia. Uh, I heard somebody talking about a phone, like it was a couple years ago, but talking about a phone number, and they said like hashtag. It's like, oh, come on, what are you doing out here? 919. Now it's not 20, it's 1A, it's 1B, 1C, 1D, 1E, 1F. Now you're out of symbols. Now you rotate back to zero. Now you increment the next one over, right? And so as we fast forward, we're at 99. 99 is not, you're not out of symbols. So this just increments 99 to 9, oops, excuse me, 9A, then 9B and 9C and 9D and 9E and 9F. Now you're out of symbols, zero, and you go here. So 9F is followed by A0, and then A1, A2, A3, blah, 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 AF. F goes back to zero. This A increments to B. Keep going that way until you get to F. Well, let's maybe say like F0, F0, F1, F2, F3, F4, F5, F6, etc. 7, 8, 9, A, FB, FC, FD, FE, FF, and then that F increments to a zero. This F has to then increment to a zero. This shadow leading zero now increments to a one. And so this 100 in base 16, let's come back here. I lost my, okay, I'm just going to type it. Okay. We didn't have just 10. Okay, I think that was 16. Yep, 16. Okay. This 100, it is 16 times. So it's this 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So now if I compare that side by side with like this 100 in hex is this many, it represents this quantity. You can see that's like, um, well, I never even did it for binary. Binary 100 would just be 4, 2, 3, 4. Very exciting. 100 in base 8 would be this many. 100 in base 12 would be this many. Base 10, this many. But you can see base 16 in just these three characters, in these three symbols, we've represented a very large quantity, much larger, because we had more symbols, more quantity per symbol. Okay. I want to change it up just a little bit. Give you a little challenge. Here's what I was thinking is I want to send you into breakout rooms. I don't think you're gonna finish it, but I would ask you to actually like try it. You can discuss if you see fit. And I'm just gonna put the challenge is like super easy. So I think I can just paste it into the chat. Okay, I hate the paste looks like trash. And I'm gonna use a gist. I think a lot of y'all like probably don't know gists exist. Um, and I have to sign in and send an SMS two-factor. Cool, cool, cool. Gist Gists are really cool. They're like a little paste board on GitHub. Fun fact along the way is every gist actually is a Git repo. Um, and you can, I like, I don't know, I find just super handy. So as I have made one very fast for you here, uh, this is going to be good enough. You can use it for code, plain text, all kinds of things. So, okay, just gonna make one quick edit right here. I must flip it to Markdown. Okay. So you should be able to open this gist URL. And what I would love for you, I included base 2, base 8, and base 16 in here. Realistically, I was thinking you might get through like one and maybe start a second one, or maybe you just fumble around with one for a few minutes. But just to get to thinking about how would we convert from base 10 to these other values. So that or these other number systems. I'm going to hit this breakout and yeah, I think about 15 sounds good. I'm gonna pull you back about 53. So you have like 13 minutes. And you also there might be a part of you where it's like, this is dumb. Don't you know I build web applications? I'll tell you, this is like even a trivial version of problems that pop up in technical interviews pretty frequently, like little manipulations like this. So good luck seeing about 13 minutes.
Better to do like a put statement or run the file and then boom, switch
And
to
then
Zoom.
boom, dropping right out. Just communicating to all those people like I couldn't wait to get out of here. As soon as the button popped up, I was like, let me away from these people.
No, no, I swear. It was a good conversation.
Good. Rest will be back here in 12 seconds. Hey y'all.
Or her name.
Um, sometimes when I'll work with Mod 4, maybe do some kind of like technical challenge like this, and then people say stuff like, oh, this Ruby, JavaScript, I forgot how to do that. Don't say that to me. Okay. If it's true, just bottle it up, put it way down, down deep. Okay. Because I didn't spend all my time and like the majority of my working life to make it so you could learn some shit. And then just a couple weeks later, be like, I basically forgot. Damn. Okay. You need to know how to do it. I mentioned this back when we're kicking off the inning, day one, state of Turing. My I think practice, like pure programming practice, is tragically missing from most of y'all's like day-to-day life. I think it's like a serious big mistake, and you would be way better off if you do a little bit of consistent practice that's not tied to your projects or not tied to any project. My favorite site is exorcism.org. I think exorcism is pretty rad. I'm biased because Katrina and I wrote most of the initial exercises available on the platform. But the thing I really like about it is that it's the two things I like about it. Number one is that it's curated and there's like a progression of exercises. It's not just like here's some random one of 100,000 random LeetCode exercises. There's a sequence, and that it's multilingual, and so you can, for instance, if you are a front end person and you've been doing some JavaScript and now you're like, oh, I want to learn about Python, you would be very wise to decide like Tuesday's my JavaScript day, Thursday's my Python day. Tuesday, I'm going to go in and do a given exercise on exorcism in JavaScript. And then Thursday, I'm going to follow up, do the same exercise, try and do it in Python. And the next Tuesday, I'm going to go do another one or something along those lines. If I was under the gun and it was like, oh, I've got 72 hours to learn how to write Go, that's the first place I would immediately, for me, and like, fair to say difference if you have like decades of experience or whatever, but I would jump right into some exercises and be like, all right, let me see how many of these I can knock out in 2 days and then read some stuff. And then I think I know Go. So please, for me, do me a favor, integrate some practice away from your projects. I know you probably didn't get super far. That's fine. Maybe it's like a little temptation to finish it up. You can post in the thread. In the events channel, I made 2 threads, one for follow-up questions or thoughts, second for some solutions. I have a flight later, probably write a solution, but I'd love to see some of your solutions. Yours probably be better than mine. That's cool. I would love it. And if yours is like shit and it works, good job. Now you're a junior developer. Um, Wrapping up this number systems talk, why do we bother? 2 reasons. One of them on the low symbol side, especially in binary, one of the reasons for using binary is that it can be represented in the most elementary means. So if you picture, for instance, like Morse code, beep, 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 like that's essentially a binary system. Either there's beep or there's silence. Okay. You can do that with like lights. You can have a light on, off, on, off. You can, because binary is just yes or no, true or false, electricity or no electricity, right? And that's what it means when we say your computer at its core is a binary system. It's because it's reliant on electricity, and the way these semiconductors and chips and logic gates and all that stuff, the way it works is there electricity? Then it's a one. If there is not electricity, then there's a zero. Flip it really fast, millions of times per second. On the other end, I think the most obvious or most understandable reasons to use a big symbol set like hexadecimal is for compression. And so I showed you that in just a couple characters, you could represent a large quantity, right? For instance, in somebody brought up the example of colors in HTML or CSS are done in hex. It's not really because it's like there's something more correct about it. It's that you can represent a greater variety of colors in a shorter number of characters. So the largest hex code is FF, FF for red, FF for green, FF for blue, right? That's 255, 255, 255. But altogether, those 6 hex digits, you can represent 16 million different colors. And so you end up with essentially like almost half as many characters. Similar argument for doing things like serial numbers or case numbers or any kind of like identifying thing like that, where you might have a billion customers. If you use more than 10 symbols, you can represent large unique values in a small sequence. So like the, serial number off a laptop that has like a mix of numbers and letters. It could be the case, for instance, that each place is allowed to have everything from 0 to 9 and everything from A to Z, which would give you base 36. And now in 4 characters, you can represent like a whole lot. I think I did the math somewhere. It says on my notes a shitload. You can represent a shitload of different quantities in 4 characters if you're doing base 36. So on the low side, base 2, base 8, whatever, those can be useful because, especially base 2, you can represent it in really simple means, and you're transmitting a large number of values, but the only possible are 1 or 2. In the large side, the larger base is helpful because you only have to transmit a couple values, but each of those values can be one of a larger set, thereby kind of compressing. That's a couple thoughts on number systems. Hope you learned a little something. Would love to chat with you on the Slack events channel. See you there. Otherwise, have a good rest of your Friday and weekend, and I will talk to you soon. Bye.